So today what we want to start with is that we're trying to understand physical properties of crystalline solids. What do we mean by that? Is a solid like this, which consists of nuclei surrounded by core electrons, and this is a lattice on which these nuclei with core electrons, which are ions, together they form the ions. These ions are sitting on these discrete lattice points. And then there are valence electrons that are moving all around. So there is an electron gas that consists of valence electrons that is all around this space. Now, if I want to understand the behavior of this crystal, I can write down the Hamiltonian for this crystal. And this Hamiltonian will have many terms. It will have kinetic energy of the ion. It will have ion-ion interactions. It will have kinetic energy of the electrons, electron-electron interactions, and it will have electron-ion interactions. In terms of fields, I can write these terms as follows. This is what we learned in the last two lectures. So these are capital size. These are the ionic fields. It's the kinetic energy. The ion-ion interaction, we're assuming it to be Coulomb interaction. Z is the atomic number. So Ze is the charge of the ion. This is the electronic kinetic energy. So small psi daggers and psis, these are the electronic fields. I've added an index sigma, which is a new quantum number, which is spin of the electron. I'm assuming ions don't have spin. They may have spin also. Electrons have spin half. So now you have two species of electrons, up electrons and down electrons. So we'll just have a sum over sigma. Then we have electron-electron interactions. Similarly, I've summed over all possible spins, sigma 1, sigma 2. And this again, we are assuming Coulomb interactions. And then the electron-ion interactions, which is given by this. So this is a very general description of the crystal. And as you can convince yourself by staring at the problem, that this is awfully complicated. So to gain insight into this, so this is our goal for the next week or so, to understand this Hamiltonian, and we'll see a lot of very interesting properties emerging from analysis of all these terms. For example, we'll see how electron-electron interactions can give rise to phenomena like magnetism and electron-ion interactions, and can give rise to, and coupled with electron-electron interactions, can give rise to phenomena like superconductivity. Thus, these ions, they can give rise to collective modes called phonons, and they help us in explaining the physical properties that we measure in the lab, like specific heat, and so on. For some of the tasks that I just listed, some of the properties, to understand some of them, you don't need to use this heavy-duty notation, but for others, you do. So what we are going to do is, so this is a very big problem. There are a lot of simple, but very relevant pieces of this puzzle which do not require this heavy-duty notation. So we'll get them out of the way first. And one such thing is band structure. You can obtain band structure of a crystal by simply solving Schrödinger equation in a periodic potential. So we'll do that first and slowly build up. And this is our final goal. So with this in mind, let's, for the moment, ignore most of these terms and only think about the ion-ion interaction. Now this ion-ion interaction has this form, but for the moment, let's only think qualitatively. Now, what happens in a solid is when you go to low temperatures, most materials become solids. And what happens is that to minimize this interaction energy, to minimize the potential energy coming from ion-ion interactions, the ions arrange themselves in a lattice, in a periodic arrangement. So this periodic arrangement minimizes the interaction energy. Now, what kind of lattice you have? Here I just drew a square lattice. In 3 dimensions, you'll have planes above and below, so a cubic lattice. Now, what kind of lattice the crystal has or the solid has, it depends on what kind of ions you have. So there are a variety of possibilities, and there are tables of possible crystal structures, and all that is a whole different field, crystallography, and there are many resources on web. I can send you an email where you can look at all the possible crystals. You can also gain a lot of insight into these using group theory, and there are a lot of tables that have already been generated. So the task at hand for you to calculate properties of some material is relatively simple because we know a lot about the symmetry properties of the various crystals that exist. Yes?
And do we know why those lattices are like that?
Yes, so it depends on the interaction energy. So the idea is you have to minimize the free energy, and what location of ions or what position of ions minimizes that energy gives you the lattice structure. But there can be many different interaction energies at play. Here I'm just writing the ion-ion interactions. One possibility is if you have, say, atoms, say covalent bonds, then there are other interactions like van der Waals interactions and some. So if you include all of the interactions and try to minimize them, you will get the crystal structure. So the problem can be even more complicated. But thankfully, we know all the possibilities just from symmetry of discrete points using group theory. And then the question is, which of the crystal, so you take a material and then you figure out using X-ray diffraction or some experimental method, what crystal do you have? You go and look at one of these tables and you learn a lot about their properties already. So next, our goal is to understand the behavior of periodic systems. So we are going to do some very simple-minded calculations, and the insights we'll gain from these simple calculations we'll put it to use later on for understanding this Hamiltonian. So to minimize these interactions, ions will sit in some periodic arrangement. So let's assume, just like there, right now I'm just drawing some points. There are no ions there yet. So the whole space that we have, this real space, we'll start with vacuum, there is nothing there. And now we put some discrete points in space. There is nothing there yet, but we keep in mind that these are the points where ions are going to sit. Let's just talk about some of the properties of these discrete points. So let's assume 3 dimensions. This is X, this is Y, and right-handed coordinate system. Z is coming out of the board. And let's assume that you have a cubic lattice. That means the distance between these 2 points is same as these 2 points, is same as the point directly above this. In that case, there is an easy way to describe all of these lattice points. How? We define a vector R. Now, this capital R has nothing to do with this R. This I just wrote down. So capital R was coordinates for ions, small r coordinates for electrons. So for the moment, we are dealing with a very simple calculation. So let's keep this aside. Now, what this R means, this vector R means, is it's called a direct lattice vector. This vector R, I'm going to write as some integer n1 times vector a1, n2 times vector a2, n3 times vector a3. n1, n2, n3, these are some integer numbers. a1, a2, a3, these are three vectors that are called primitive lattice vectors. So this is just notation. What do we mean by this? So for this cubic lattice, you can choose A1 to be the distance between the sides. Let's call this A, small a denotes the distance between the sides. So this distance is A. So we can choose A1 to be AX hat, A2 to be AY hat, and A3 to be a Z hat. Let's choose origin to be at one of these points. Let's say this one. Now you can see that, so this is our origin. With this being origin, which corresponds to one choice of R, which is 0, 0, 0, you can access any of the points by a choice of n1, n2, n3. For example, this point is 1, 0, 0. n1 equal to 1, n2 equal to 0, n3 equal to 0. This is 0, 1, 0. The point above it is 0, 0, 1. This point is 1, 1, 0, and so on. So what that means is that this vector R spans the whole direct space. By direct space, I mean the space we are starting with, the real space. So all of these points are spanned by direct lattice vectors, or the lattice vectors. And the lattice vector R is written in terms of primitive lattice vectors. So this is just some notation. So these capital R's are the direct lattice vectors that span the whole space. Now, another interesting thing that you can already guess is the periodicity, which basically means that if you're standing at origin and you look around, you see a lattice, space around you. If you move yourself by any lattice vector R, say you move to a point over here, and you look around, you see exactly the same thing. So this crystal is invariant under translations by this direct lattice vector R. Right? So far everything is empty. We just chose these points, and we can finally we'll put ions at these points. Sometimes in some crystals, instead of one ion, you can have a group of ions corresponding to each site. This is called basis for the crystal. We're not going to do it here, but in the next tutorial, you'll do a problem where you will have a basis. You'll have two atoms. It will be a covalent structure, graphene, where you will have two atoms per side. And you'll see that it can have important consequence. In graphene, it particularly gives you a relativistic dispersion relation. It has interesting properties. But for now, we can keep it simple, and we'll assume that one ion will eventually sit at these lattice sites. Now, because we are dealing with the periodic systems, it's often convenient to go to Fourier space. So this is direct space, and we know that in direct space we have discrete points, and the system is periodic. There is symmetry corresponding to translation by a lattice vector. Now, so it's very useful. It's a periodic system. It's useful to go to Fourier representation or the Fourier space. So this has discrete point. So the Fourier space must also consist of discrete points. So now what I'm drawing is discrete points in Fourier space. So let's say this is direct space. This I will call it, it's called reciprocal space. Sometimes it's also called K space or Fourier space and so on. So what it means is just the Fourier transform of direct space. So the Fourier transform is also discrete set of points. Now I'm drawing it like this, but the scale can be very different for the direct space and the reciprocal space. So all of these points in reciprocal space are spanned by what is called reciprocal lattice vector, which is denoted by G. So this is direct lattice vector that spans the direct space. These are reciprocal lattice vectors, which are defined. So these are reciprocal lattice vectors. These are direct lattice vectors. So these reciprocal lattice vectors, they're defined using this property that e to power g dot r is 1. So any vector g that satisfies this is a reciprocal lattice vector. Moreover, this reciprocal lattice vector G, this can be written as M1 B1 plus M2 B2 plus M3 B3, where again M1, M2, M3, they are integers, and B1, B2, B3 are now similar to this. These are primitive reciprocal lattice vectors. Yes?
How do we know that the reciprocal lattice is also cubic?
So, for example, we don't assume. This is, use this definition and you can prove the symmetry. There are, yes?
Where does that definition come from? Where can we derive it?
So you can derive it by, again, this constraint. First, that e to power g. So you have this, you can span this entire lattice by this vector. And then when you do the Fourier transform, so right now we are not, space is empty, but this really comes from the definition of Fourier transform. So as soon as we put something in and do Fourier transform, it will become very clear. So it's similar to, this e to power I k dot r factor for Fourier transform. So it comes from there. And K space,
right?
Sorry?
It's a condition of periodicity, right?
Yes, exactly. So it's nothing but because the system is periodic and this is Fourier space, this is the definition. So next, what we would like to do is in 3 dimensions, there is a simple formula. So what we are doing right now is very elementary vector calculations. I'm not going to go through the details. It's useful to do it once, so whenever you find time, do it. But it's useful to know this. It really helps the discussion to understand this big problem. So it's worth doing it once. Now, you can, using this definition, for 3 dimensions, you can derive formulas for reciprocal lattice, primitive reciprocal lattice vectors, B's, in terms of A's. And this B1 is 2 pi A2 cross A3, A1 dot A2 cross A3, and likewise. So this is a description in 3D. Equivalent formulas you can derive in 2D and 1D. A particularly important relation exists between the primitive reciprocal lattice vectors, those are these B's, and the primitive direct lattice vectors, the A's. And this we will use repeatedly. You can verify this for 3D by these formulas, and likewise for 2D and 1D. And let me just write down this formula here. And this we will use repeatedly in our description. So Bi dot Aj is 2 pi delta Ij. So what it really means is B1 vector is orthogonal to A2 and A3, and B1 dot A1 gives you 2 pi. So B2 vector, so this is really, in some sense, it's a convention. You choose to make life easier, will always choose reciprocal vectors, primitive reciprocal lattice vectors. So first, there are many possible choices for primitive direct lattice and primitive direct lattice vectors, and correspondingly the primitive reciprocal lattice vectors. But we will use the convention. We'll derive these. We'll keep in mind that these are the formulas that we'll use standard notation, and what we'll really use is that the primitive reciprocal lattice vector B1 is orthogonal to A2 and A3. Similarly, B2 is chosen so that it's orthogonal to A1, A3, B3 orthogonal to A1. This you can directly see in this formula. B1 is cross product of these two, this is cross product of these two, and so on. So it's very easy to verify this using these formulas. So this we are going to use repeatedly in the course. And now so there are many possible examples of these crystals. Let's consider one very simple example, which is particularly useful. So in the tutorial, you'll discuss honeycomb lattice. What does this lattice really mean? So in 2D, let's consider what is called hexagonal or triangular lattice. So what this really means is you have a triangular lattice like this, and so on. Now, from a triangular lattice like this, you can obtain a hexagonal lattice by removing the points in the center of a hexagon. So from this triangular or hexagonal lattice, so what I'm going to draw next is honeycomb lattice, which is simply a lattice like this. So you can keep drawing, and that will be the. So you will do, the key point that I want to make is keep in mind that the number of neighbors that one point has can vary. In this case, each point has 6 equidistant neighbors. In this case, each point has 3 neighbors only. By neighbors, I'm only talking about nearest neighbors. So this point, each ion will have 6 nearest neighbors in this case. Each ion will have 3 nearest neighbors in the honeycomb case. And this is what you will discuss in tutorial. So for the moment, let's take this hexagonal lattice and let's try to let's choose coordinates. Now what I'm going to do is I'm going to start here and I'll say that this is my primitive lattice vector A1 and this is my primitive lattice vector A2. We are doing these simple examples just so you gain some insight and it will help us a lot in what is coming next. So this A1 vector can be written as A times 1, 0 or A x hat, where A is this distance. So this distance between 2 points is A now. So the vector A2, this is a triangle with all sides equal, angle is 60 degrees. So we can write this as cosine pi by 3 sine pi by 3. So A half square root 3 by 2 or also A by 2 x hat plus square root 3 by 2 A y hat. Now you can check that if this is your origin, all of these points can be spanned by direct lattice vector R, which is now n1 A1 plus n2 A2. So this point, for example, is just n1, n2 being 0. This point is 1, 0. This point is 0, 1. This point is 2, 1. This point is 1, 2, and so on. So choices of these integers n1 and n2 will ensure that these direct lattice vectors span this whole lattice. Next comes the reciprocal lattice vector G. Now G is m1 b1 plus m2 b2. How can we find b1 and b2? So this is formula in 3D. In 2D, let's start with the definition. E to the power I G dot R is 1. That means E to the power I M1 N1 B1 dot A1 Now this should be 1. Again, we'll use that the reciprocal lattice vectors and direct lattice vectors have some orthogonality between them. So B2 is orthogonal to A1 and so on. So if B2 is orthogonal to A1, this will drop out. B1 is orthogonal to 2, this will drop out. That simply means Okay, so B2 dot A1 should be 0. That implies that B2 vector, this must be, A1 is along X, so B2 must be along Y. You can assume that this is some beta times Y, and then use B2 dot A2 is equal to 2 pi, and this would imply, now this is square root of 3 by 2, this would imply that beta square root 3 by 2 A is 2 pi. This implies that beta is 4 pi over square root 3 A. Right? So I just use this formula to calculate B2. Now, similarly, you can assume B1 is some general vector, B1x times x hat plus B1y times y hat. Go through this calculation and you will find that the vector B1 will come out to be 4 pi square root 3a square root 3 by 2 minus 1/2. So I have A1, A2, I have primitive reciprocal lattice vectors B1, B2. So I have a description of the direct space and description of the corresponding K-space reciprocal space or reciprocal space. So now we are going to assume that ions are sitting on these sites and these ions do not move. So we are ignoring the kinetic energy of the ions. Very simple calculation. And let's assume now one single electron is moving through this space. So you have discrete set of points occupied by ions and one single electron is moving through this space. Now this electron will see the potential, the electrostatic potential created by the ions. And this electrostatic potential will have the same periodicity as the periodicity of the lattice because ions are giving rise to this potential and the ions themselves are arranged in a periodic way. So the potential they create is periodic with same periodicity. So what that means is now we are interested in solving one single electron going through this space occupied by ions at discrete lattice points. If I write down the Schrodinger equation for this one electron that sees this potential, the equation would be following. So the Hamiltonian describing one single electron moving through this periodic ions is minus h bar square over m del squared, this is the kinetic energy, plus some potential energy u of r. Now this potential u of r is periodic. So this potential u of r should be same as the potential u of r plus capital R for all r, where r is a direct lattice vector. So this is simply one single electron moving in periodic potential. Now, it is useful to define an operator which is called the translation operator. So let's define a translation operator TR, which is it translates by the direct lattice vector. So this TR is the translation operator which acts on a function of coordinate r and it shifts the argument by the direct lattice vector r. Right? So this is just a definition of the translation operator. Now you can verify the translation operator with direct lattice vector R acting, so let's say R with R prime f of R is same as TR prime TR acting on f of R is same as T R plus R prime acting on f of R, because all of these simply give you f R plus R. So you translate by R prime first, f of R plus R prime, then translate by R, you get this. You translate in reverse order, you still get this. You translate by R plus R prime, you still get this. So what does this mean? This simply means that these two operators commute. TR prime, they commute. Now we are going to discuss more properties of this translation operator. Let's consider this quantity. Translation operator TR acting on HR multiplied by psi R. This is useful because eventually we are interested in the eigenstates of the Hamiltonian. So TR acting on HR psi R, this simply gives you HR plus capital R psi R plus capital R. Now what is HR plus capital R? Now H of R plus capital R, you can convince yourselves that this is same as H of R. Why? You have a gradient that acts with that's derivative with the coordinate R, d over d small r. You're just shifting with capital R, so the derivative term, it's just a constant. It remains same. U of R plus R is same as U of R. So H of R plus R is same as H of R. This psi of R plus R I can write as the translation operator R acting on psi of R. This implies that the Hamiltonian commutes with the translation vector for all R. Right? What this means is that I can choose eigenstates of Hamiltonian that are simultaneous eigenstates of the translation operator. So I can choose eigenstates of the Hamiltonian such that they are also eigenstates of translation vector for all R. So let's call these eigenstates psi. So you have H psi R, this is E times psi R, and because these are simultaneous eigenstates of the translation operator, you have psi of R. This is the eigenvalue, corresponding eigenvalue for the translation operator. Right? Now, these eigenstates psi of R must be normalized. That means that the integral d cube R mod psi of R square, this should be 1. Now in this, let's make a substitution. R, it goes to R prime plus capital R. This would mean that integral d cube R prime psi R prime plus R square is 1. So we are integrating over all space, and if you're worried about the boundary of this space, we are using periodic boundary conditions, so closing the system in a ring, in a one-dimensional system in a ring. So this substitution, the integral over d cube r, this just gives you d cube r prime, integrated over all space, and this must be 1. This implies, yes, you have a
Sorry, I have a question there when we're doing the translation to H phi.
Yes.
Psi, sorry. We can think of H psi as a function, and then we translate it. But we can also think of translating, like doing inserting an identity in the middle of H and phi, right?
Yeah.
And then to transform an operator, we need T R and T of minus R to transform the operator.
So this right now, we are thinking of this as a vector. So I get your point. You can also think of translation for Hamiltonian. You can construct those operators.
I was confused. Okay, thank you.
So this is just acting on a function for the moment. Yeah. So we have this equation here. Now this implies that now I'm going to write this as T of r psi of r prime. Now this T of r acting on psi of r prime is, that would mean that, let me just write down the result here, C of r mod square So what that means is that the eigenvalues of these translation operators are some phase. They can always be chosen as some e to the power I theta, where theta is real. Right? So we made an important conclusion, and this will lead us to what is called Bloch's theorem. So these eigenvalues are such that they can be chosen as a phase. Right? So what do I mean by that is I can write, so now it's a matter of choice. So C of R, where R is a general direct lattice vector, this modulus square should be 1. So we can always write C of AI. So AIs are the primitive lattice vectors. I can always write C of AIs as e to the power 2 pi I xi, where xi's, x1, x2, x3, these are some real numbers. So keep in mind that this must be true for all R, right? And now I'm taking the special case where this R is a direct lattice vector AI. For these special cases, I can write down this CAIs as e to the power 2 pi I xi, where xi's are some real numbers. Now, for an arbitrary lattice, direct lattice vector R, you have n1 a1 plus n2 a2 plus n3 a3. Now you can check that T of R prime, or let's say T of R prime, T of R acting on psi of R. This is same as T of R prime acting on C of R, psi of R, which is same as C of R multiplied by C of R prime times psi of R. Right? Also, if you have C of N1 times, say, A1, that means using this, you can show that this is same as multiplying C of A1 with C of, so this is nothing but C A1 plus A1 and times with simply C A1 to the power N1. So it's simply because these property of these translation operators, you have, if you translate by R and R prime by two different arguments, the eigenvalues, these are phases, they multiply. It's just a property of the exponential function. It means you can write this. So what this really implies is that the eigenvalue of the translation operator for a general direct lattice vector R can be written as CA1 to the power N1, eigenvalue for A2 to the power N2, and eigenvalue for A3 to the power N3. Now this is equal, this is precisely equal to C of R is being e to the power I k dot R, where k is x1 b1 plus x2 b2 plus x3 b3. So now what we are doing is we are showing that the eigenvalues of the translation operator can be written in terms of a vector in reciprocal space. So we choose this as the eigenvalue, and that means the eigenvalue for the general vector is this. This can be written as a vector k dot R, where k is a vector which is x1 times b1, x2 times b3, x3 times b3. x1, x2, x3 are some real numbers, and b1, b2, b3 are primitive lattice vectors for the reciprocal space. So k is a vector in reciprocal space. That is this vector here. And this vector k need not be, so if you start in this origin here, this vector k need not take you to another lattice point. It can take you anywhere in space because x1, x2, x3 are real numbers. And this vector k is what we'll refer to as quasi-momentum. And this vector k will be used to label the eigenstates of the Hamiltonian. So we can quickly show this how, well, what does e to the power I k dot R mean? This would simply mean that e to the power I x1 b1 plus x2 b2 plus x3 b3 dot n1 a1 is the same as C of R. because this is same as this. So this particular choice was made so that we can relate the eigenvalues of the translation operator with a vector k, which is called Bloch vector in reciprocal space. So the eigenvalues of the translation operator can be written in terms of e to the power ik dot r. R is a vector in direct space. R is direct lattice vector. K is a vector in reciprocal space. Because the eigenvalues of translation operators are just phases, you can always write it as a product of a vector in reciprocal space and a vector in direct space. So that's all we have done here. We have written the phase, which is the eigenvalue of translation operator, as a product of a vector in direct space and a vector in reciprocal space. Yes?
So my question is the following. How can we see that these energy eigenstates are also eigenvalues for the translation operator without imposing it at the beginning?
The eigenstates. This is so. It just yeah, but I think also crucially they are for all R.
Okay. Thank you.
So that's basically what we have done. This is just some can be chosen as phases. So keep in mind the translation operator eigenvalues are really just phases, and you can write this phase as a product of two vectors, direct space and lattice, and reciprocal space. And now using this property of the translation vector, we can write down an equation which is known as Bloch's theorem. So what I can write is translation by a direct lattice vector R on an eigenstate psi of R. This should translate the argument R. This is same as psi R plus R. Also, this should be same as the eigenvalue of the translation operator times this. These are simultaneous eigenstates. So this is same as C of R, psi of R, which we just shown that this is same as e to the power k dot R psi of R. That implies that psi R plus R is e to the power I k dot R psi of R. This is called Bloch's theorem. Now, one thing about this equation here, so just for, we can generalize this result by putting in some additional quantum numbers, which will be handy later on. So this is Bloch's theorem. The eigenstates are this factor e to power I k dot R times the eigenstates. So these eigenstates on the left-hand side, they are translated by direct lattice vector R. You have Bloch vectors dotted with that direct lattice vector, and you have the argument here, R. Now, what you can note in this equation is that the k does not appear in the argument here. So left-hand side does not have k anymore, does not have k to begin with. It does not appear in the argument, right? But it appears on the right-hand side. So k, because it does not appear in the argument, it must be a label. And we'll use k to label these eigenstates. Also, there can be additional labels, additional quantum numbers that we have not considered here. So just for the sake of generality, I'm going to put in some quantum numbers in just notation. And if they are redundant, later on we'll see that they play no role. So what I'm going to write down is Bloch's theorem with some additional quantum numbers n and k. So I've really done nothing but just added some labels, some quantum numbers for eigenstates. Now this index n, so k should be there as we discussed, but this quantum number, additional quantum number n, I've just added because later on we'll see this will become what is called as, what is known as band index. So any questions so far? And this is now, this is called Bloch's theorem. Yes.
Does the quasi-momentum has a physical meaning?
Yes. So it is essentially, it is momentum, but for periodic systems, what you have to do is you don't have to solve the problem in entire momentum space, but you can solve the problem in a much smaller space, and by translations with some vectors, you can have information about the whole space. So, for example, so this K is a label. You can just call it momentum label also if you wish. Quasi is typically added in convention when there are some exceptional cases, especially dealing with boundaries. But for most purposes for the moment, you can think of this as momentum. So you have direct space and its Fourier transform is momentum space, for example. And that also suggests that you can use this to label the eigenstates. Now, just for completeness, there is another formulation of Bloch's theorem, and that is what we are going to do next. So this other formulation says that these eigenstates psi n k of R what this formulation of Bloch's theorem says is that the eigenstates of an electron in a periodic potential can be written as a plane wave. Now notice that this is the coordinate here, a plane wave times a function, and this function u and k has the same periodicity as that of the lattice. So this is, let's call it second form of Bloch's theorem. Now this, we can simply show that these two forms are actually equivalent. We can derive this using the first one. So how can we do that? It's quite simple. We can start with saying that psi n k r is e to power I k dot r times some function. Now this I can always write. I have some function on left hand side. I can write it as some plane wave times another function. The goal is to show that this function has same periodicity as that function, as that of the lattice. So this function must satisfy this property. Now consider psi n k r plus r. So I can, again, because I'm writing this as exponential times some functions, that means this should be same as exponential k dot r plus r times u n k r plus r, right? Now, from this version of Bloch's theorem that we just proven, I can write psi n k r plus r as e to the power I k dot, now it's the capital R times psi n k r. Now, what is psi n k r? I'm using this substitution. So let's substitute that. That is same as e to the power I k dot r plus r times u n k r. That means I've just shown that this function is same as this function, so it must have same periodicity as that of the lattice. So next what we are going to do is we are going to do translations in reciprocal space. Now consider, so far we have considered translations in direct space. Consider this quantity n k plus g. Let's apply Bloch's theorem to this. This means that e to the power I k plus g dot r should be psi n k plus g right? Now, by definition of reciprocal lattice vectors, this is same as e to the power I k dot r psi n k plus g r So what have we shown? We've shown that psi n, a translation by reciprocal lattice vector, actually does nothing. Now compare this with the earlier formulation. So if you translate by a reciprocal lattice vector on this equation, you get this equation. You see that nothing, no other fact, this factor does not change. So the information contained in the eigenstate psi n k, physically both of these psi n k and psi n k plus g, they obey the same equation. So the physical information that is contained in psi n k is same as the physical information that is contained in psi n k plus g. Using this concept, we can define what is called first Brillouin zone, and that will mean that we don't have to solve the problem for the entire momentum space, but we can solve it for a small restricted momentum space. And this will be called as first Brillouin zone. So let's do this. So let's do this for a very simple case. Let's take, again, 2D. Let's take 2D squared lattice. So the primitive lattice vectors are ax hat, ay hat. This distance is a. That means the direct lattice vectors are n1 a1, n1 a1 plus n2 a2. Now I can find the reciprocal lattice vectors G as m1 b1, m2 b2. Now this is fairly simple. We want b2 to be orthogonal to a1 and b1 to be orthogonal to a2. So you can find, so b2 must be along y, b1 must be along x, and then you can use again this equation to find out exactly what they are. So this would mean that b1 is simply 2 pi by a x hat, and b2 is 2 pi by a y hat. So now I'm going to draw the reciprocal space which will be spanned by all g's. So this is the reciprocal space. This is G equal to 0, reciprocal lattice vector G equal to 0. So this is the origin. Now what I'm defining is first Brillouin zone, and the reason we are defining it, or the way we will define it, is the entire space, or the space or the points in the space which are closer to G equal to 0 than any other G. So what I want is to make a space around G equal to 0 which consists of all points which are closer to G equal to 0 than any other reciprocal lattice vector. So this is G equal to B1. This is G equal to minus B1. This is G equal to B2. G equal to minus B2. This is G equal to B1 minus B2. This is G equal to minus B1 minus B2, and so on. So the space of points, all points that are closer to G equal to 0, then let's say, then this vector is basically all points that are below this line. Then you want to find all points that are closer to G equal to 0 than this point. That will give you this space. Then similarly, you will get this space here and this space. So this space is called first Brillouin zone. Why is this important? So this is very simple case, square lattice. If you have a complicated structure, you still go through the same analysis. You connect G equal to 0 with all other G's, and you consider the whole space that is closer, all points that are closer to G equal to 0 than any other G. Using this definition, you can define a region of reciprocal space, and this region of reciprocal space is called first Brillouin zone. So what that means is for all vectors Q in reciprocal space, there exists a K in first Brillouin zone and a reciprocal lattice vector G such that Q is equal to K plus G. That means, so this is what we really want to do. So any point in reciprocal space, say some point over here, it can be written as some point over here plus some reciprocal lattice vector. What that means is if you're interested in finding psi and q of r, that is, the momentum can be any vector in the reciprocal space, this can always be written down as psi n k plus g of r. And we have just seen that this state, the physical state, is equivalent to psi n k. So we just need to solve the problem, the eigenstate. We just need to calculate eigenstates in this region, in the first Brillouin zone. And then by translating by a reciprocal lattice vector, we have obtained the solutions in the entire space. Any questions so far? Yes.
We showed that psi of n k plus g transforms in the same way as psi of nk under translations, but we didn't show that those two functions themselves are equivalent, did we?
No. So what we have shown here is we just compared these two equations, and we are saying that these obey. Just keep in. Okay, let me simplify it further. In the beginning, we didn't have any labels, right? These labels we put in the end to label the eigenstates, and we are choosing this label K in the reciprocal space in such a way that this G obeys this property. So let me try to rephrase it. So for any general vector, I understand that this can be very different. But these translations, so we are comparing these two states, psi n k and psi n k plus g. So if you translate by some random vector, the state can be very different. All we are saying here is you take a momentum and translate this momentum by a reciprocal lattice vector. Just because the system is periodic, the reciprocal lattice is also periodic. Reciprocal space is also periodic, and the eigenstate will have the same physical information. But I think what you're saying implies that if you have a general vector, we have not shown that, and in fact, that can be very different. So next, we want to, so far we haven't really solved the equation, but we have discussed some general properties of the Schrodinger equation in the presence of a periodic potential. Now, there are two models, two extreme cases where we will solve this problem of electrons. We'll solve this Schrodinger equation basically. Now, the first case is we are going to consider perturbation theory. So, where is the Hamiltonian that we wrote? So what we will consider is that top line over there, we can imagine that the periodic potential is very weak over there. And we are going to do perturbation theory and see the effect of this periodic potential. And in another limit, so this will give us the band structure. Another limit is where we consider that electrons are tightly bound to these ions. And if they are tightly bound to these ions, we can describe them by what is called a tight binding model, where all that can happen if you have lattice sites and assume that the electron has to be tightly bound to a lattice site, all that can happen is this electron can hop around. Electron can be, so only dynamic process that we allow for in this model is that electron is tightly bound to this, and by some process it can jump here, but it will then be tightly bound to this, or it can jump here and be tightly bound to this. And for this particular case, we'll use the notation of creation and annihilation operators. What that really means is, what is hopping? If an electron hops from this side to this side, you destroy an electron here and you create an electron here. So in this way, we'll be able to write down the Hamiltonian of the system and then solve it to get again the band structure. So what I'm going to do next is I'm going to start something which I'm not sure if we'll be able to finish, but let's start anyways, and we'll stop in 5-10 minutes. So let's consider the first case where we want to use perturbation theory. So this we'll call this is usually referred to, this model is called nearly free electrons. And for simplicity, let's just assume that we have one-dimensional lattice. So this is a one-dimensional system. The distance between these 2 points is A. So we have, this is along X. So the direct lattice vectors are N1 times A1. A1 is AX hat. The reciprocal lattice vectors, these are M1 times B1, where B1 is 2 pi over A times X hat. So very simple case, it's a 1D lattice. Now, an important thing to consider is the boundary conditions. So for some cases, you would like to consider this lattice, it's finite, and then you would like to consider open boundary conditions. And that we'll discuss later. For moment, what we are going to do is we are going to assume periodic boundary conditions. What does that mean is, if there are, say, capital N sites, 1, 2, 3, so capital N, we are going to identify the N plus first site to the first site. So we are going to assume periodic boundary conditions. Which means that the N plus first site, N plus first lattice site is same as the first site. This also corresponds to closing this one-dimensional lattice in a ring. So if this is first side, this second side, this third side, this is n, n minus 1, n minus 2. So if you add to any side n sides, you get back to the same site. So this just means that we have imposed periodic boundary conditions. Now, these boundary conditions are going to have some important consequence for this block vector k. So now another thing we can do quickly is we can calculate the first Brillouin zone in this case. So this is the direct lattice. We have the reciprocal lattice vectors. Let's draw the reciprocal lattice. Reciprocal lattice is also a one-dimensional lattice. This is reciprocal lattice. So this is G equal to 0. This is G equal to B1. This is G equal to minus B1. How is the reciprocal lattice defined? All points that are closer to G equal to 0 than any other reciprocal lattice vector. So all points between this and this is the first Brillouin zone. So B1 is 2 pi over A. So this is simply pi over A to minus pi over A. So if this vector k is between minus pi over A, so the block vector k, this is along x-axis. Also, it's a one-dimensional system. And if this k is between minus pi over A to pi over A, then this k belongs to first Brillouin zone. Now, these periodic boundary conditions will have some consequence for this k. We can do this by just applying Bloch's theorem. So let's do that, and then we'll stop. So we have psi of k r plus capital N times A is equal to psi k of r. This is from boundary conditions. If you add to any point, NA is the total length of the system. So A is this vector, n times A is the whole system. If you translate, so because it's a one-dimensional system, we don't have to burden ourselves with these vectors. They're all along x-axis. NA is the total length. If you translate the system by R, you get back to that point. This is the periodic boundary condition statement. Now let's apply Bloch's theorem to this. That means this should be equal to e to the power I k dot NA. It's a one-dimensional system. I, k, and A, psi k of R. This implies that e to the power I k and A must be equal to 1. That means Ka must be K must be 2 pi over capital N where the small n belongs is some integer. So by imposing periodic boundary conditions, what have we achieved? If we impose periodic boundary conditions, the vector k is now quantized. what this imposing this periodic boundary conditions means is that this Bloch vector K can now only take discrete values which depend on the total system size. So if the system size number of sites is very, very large, essentially it's a continuum. But for a finite system in general, imposing periodic boundary conditions quantizes the values of K that the system can have. Now K must, if we are interested in the first Brillouin zone and we want this K to be between minus pi by A and pi by A, this implies that 2 pi over NA that means you can, this index n is between capital N by 2 and minus n by 2. So what have we really done? Well, we are only going to solve the problem in the first Brillouin zone. We impose periodic boundary conditions and that quantize the values of this Bloch vector within the first Brillouin zone, and the values of n that are allowed such that the vector K is within the first Brillouin zone are that this integer, small integer, must be between minus n by 2 and capital N by 2. So tomorrow we will solve the Schrodinger equation using perturbation theory and see what is the consequence of this periodic potential.